So this is a joint paper with Yingni Guo. And if you want to upload a paper to your memory that is related to the paper, then the paper to think about is Armstrong and Vickers 2010, but I will also tell you about it in a minute. So this is a story about two characters, an agent and the principals. And these two guys need to pick a project together from a set of available projects. They both want to implement some project, but they may have some different interests. There may be projects that the principal likes more, or there may be projects that the agent likes more. And both of them, each of them has some bargaining power. The agent is the only one who knows which projects are available. The principal is the one that in the end is going to decide which project will be implemented. And as an example to keep in mind, which I don't claim is an application, it's just an example. The principal is a dean, the agent is a department, and projects are possible candidates to hire. The department gets a lot of applications. From these applications, the department pick one, present it to the dean, and the dean decide whether to accept or not accept the recommendation, whether to hire this person or not.
This meeting is being recorded.
Perhaps there's something weird happens in my Zoom, I don't know. And perhaps the department and the dean care a bit about different things, right? The department cares more about research, the dean maybe care more about teaching or diversity. Okay, so I'm going to jump into the model. A project is given by a pair UV. U is the utility for the agent, and V is the utility for the principal. And this, the world of all potential projects, I will denote it by D. And in this talk, I will assume that it's a rectangle with some lower boundary for the utility of the agent. And both of them are, both of these guys are in von Neumann-Morgenstern utility maximizer. So this is just a rectangle. And I'm picking a rectangle because it's the simplest thing in which some interesting things pop up. If no project is implemented, both get 0. So as I said, both of them would like to implement some project. So in principle, why would the principal reject any, veto any project? Well, the reason the principal has to threaten the agent with a veto power is because the principal is worried that the agent will only care about what the agent likes and not about what the principal likes. That's why the principal needs his veto power. So the way the process will go is there is a set A of available project. Known to the agent, but not to the principal. The agent proposes a project from A. And when I said verifiable proposal in my title, what I mean is that you can not invent projects that are not actually available. And the principal accepts with probability eta UV. That depends on the project. And I forgot to tell you that this is a mechanism design problem. So before everything starts, the principal commits to eta from D to 0,1 to the probability of acceptance. given these two things, we know now how
now,
the agent will pick.
A is an arbitrary subset of D.
A is an arbiter is a set of D. Yes, known to the set of available
Yes.
projects known to the agent and not to the principal.
And no assumptions on A. It's in any subset.
Yeah, any finite, let's say.
Okay.
And it's not
finite subset. Okay.
finite subset. Yes. And it's clear how the agent will pick UV. He will pick UV that maximizes his own payoff. Right? Maximizes his own expected payoff. This is how the principal will pick UV. This is how the agent will pick the UV that he proposes. And the principal's payoff is going to be, under this mechanism, is going to be V times eta UV. This is the principal's payoff. Compare this payoff to what the principal could have gotten if there was no income, if there was symmetric information. If the principal would also know the set of available projects, the principal could have gotten V, because the principal could have gotten, sorry, if the principal knew the set of available projects, the principal could have gotten maximum of V over all the projects that are available. This is what the principal could have gotten. Sorry, I'm going to call it the complete information payoff. This is what the principal could have gotten if he knew what is the set of available projects. And the difference between these two things is called the regret of the principal. The regret depends on the mechanism and on the set A of available projects. Okay. The principal will suffer some regret. The regret is the difference between what the principal could have gotten if he knew what is the set of available projects, why he could have gotten it, because he could have said, look, I know the set of available projects. I know that the projects that is best for me give me 10. I will only accept the project if you offer this thing. Sergio, I think you are talking and I don't hear you.
Can't be 10, has to be less than 1, but doesn't matter. By your assumption.
Right. Okay, yeah, but you got the message.
Just to show that I'm following, just to show that I'm following.
That's great. So the principal could have, if the principal knew, he could have guaranteed the best payoff in the set, right? The difference between these two things is what I call a regret. Actually, not I call regret, right? It's a common term. I should mention that the term regret is not that intuitive here. It's a bit misleading because I never assume that the principal actually know what is the set A of available projects. So it's a bit weird. Usually we think about regret as something that you learn in retrospect. Here, I do not assume that the principal know the set of available projects. And indeed, the thing that I call regret was called loss by Savage, but I'm using the more modern term, regret. The principal is trying to pick the optimal mechanism. Now, what does it mean, optimal mechanism? I mean, the regret obviously wants to minimize his regret, but the regret also depends on this set A. So the standard approach in mechanism design is to say, okay, the principal doesn't know the set of available projects, but when he doesn't know something, he has a prior over these things, and he's trying to minimize his expected regret, right? This is the standard approach in mechanism design, to minimize expected regret, or equivalently to maximize expected payoff. And this is what the paper by Armstrong and Vickers did, which I will get to in a minute. But what we are doing is something else. We are doing what Savage called min-max loss, and today and nowadays is called worst case regret. We define the worst case regret of a mechanism eta as the maximal possible regret that you can suffer. And the principal goal is to minimize worst case regret. Minimize the worst case regret. Find the mechanism that minimizes worst case regret. Okay, so I think I'm done with the model. I'm going to give you a related literature slide. This is a good time to ask questions if you have something quick about the model. In a minute, I'm going to describe to you the optimal mechanisms. Let me just tell you that you will see in a minute that in the Bayesian approach, there is almost nothing we know how to say because it's actually a very complicated mechanism design problem. There are no transfers here, and the set of types, the set of possible A's is a huge set, right? It's not one-dimensional now, it's a type is a subset of projects. So you have to think about distribution over subsets. It's not a creature you see often. It's not really easy to define. So they are very limited what we can do with the Bayesian approach. With the worst case regret approach, you can do a lot. In particular, we will solve for this problem. We can also solve a more general problem in which the agent proposes a set of projects to the principal, and the principal picks one of them. This is more complicated than what I present today. And if you're interested in this, you can come to Yingni's talk next week in the workshop on learning, and she will talk about that. But I'm going to concentrate on this model where the agent can propose only one project. And my main focus would be what we gain from the fact that the principal also observes the payoff of the agent. So my main focus of this talk would be what we gain from the fact, why is it important to the principal to also observe to also observe the utility of the agent in the project that the agent offers, right? So this will be the main issue of this talk, and I will, in order to focus on this, I will also solve another problem, another mechanism design problem, in which when the agent makes a proposal, the principal can only observe the principal utility from the project, not the agent's utility from the project. And I will see why it matters. Okay, so I had a related literature slide. Let's see if I can. Shit, do you see it? You see it? You're supposed to see like slide of related literature. Yes, I think you see it, right?
No.
No, we see what's on your iPad. Oh, there it is. Wonderful.
Okay. This is the, okay. So this is the paper that is most related to us, the paper by Armstrong and Vickers. While we wrote this paper, we noticed also a relation which is very strong to the literature on mechanism design with evidence. This will not pop up so much in my talk, so I'm not going to talk about it, but if you go to Yingni's talk next week, you will hear more about it. And in general, there is a lot of literature, there is now some literature about mechanism design with worst case objectives, in particular the mechanism design with worst case regret. Apparently the kind of the original papers which we found are this paper by Horowitz and Shapiro and the paper by Bergman and Schlager. Okay, so I'm going to describe to you what was the conclusion of Armstrong and Vickers. Armstrong and Vickers, as I said, did my exercise, but with in Bayesian setup. So first you have to define how to think about prior over subsets. They assume that projects, that the number of projects, number of available projects has some distribution over integers like Poisson or geometric or whatever, and projects are IID from distribution over D, some distribution over D, over the same D that I had before, the rectangle, and independent of their number. So first God decide how many projects will be available, and then God randomize the realization of the projects independently of their number. Okay, and under this conclusion, under these assumptions, they got two things. Sorry, and the
So that's for both?
Sorry, I didn't hear.
Yeah, so for both the principal and agent, they draw a U and a V like you?
Yes, but the U and V can be correlated. The projects, the available projects are independent between themselves, but there might be a correlation between the payoff to the principal and the payoff to the agent. Did I answer you? I don't.
Yep.
Okay. And under this assumption, they got two things. And with these assumptions, it's still a difficult thing to solve, but they also made the assumption that only deterministic mechanisms. Only deterministic mechanism means that a mechanism is just a subset. A mechanism is just a subset is given by a subset of the set of potential projects. These are the subsets which I will accept, and everything else I will reject. And the agent, if the agent has something from this subset, he will offer the one that is best for him. And if not, then no, nothing will be implemented. Okay.
So just to see if I follow, if there are a lot of projects, if the set A is big, then in a sense he can get within epsilon of the optimum by just saying, look, I'm not going to accept anything that is.
But he doesn't know.
So, epsilon below the maximum get, right?
But the principal doesn't know the size of the set. Right? I mean, it's true if the distribution was such that with high probability the set would include many.
Be large, then he could do that. But of course, the problem is interesting for small sets.
Yeah.
What I'm saying
is interesting
large
in their case, it's interesting only.
Okay.
Yeah.
Good.
It's even interesting, I think, if he knew the size and the size was not big. So if you knew that the size is 3, it's still interesting. But you're right. So this is a mechanism, right? And this is why it's essentially a delegation problem. Right? Delegation, it means that the principal tells the agent you can choose one of these things if you have this action, and otherwise nothing. And their solution is that T has the form. So their theorem is that optimal T is of the form UV such that V is greater from some function of U. So R is some threshold function, and V is greater than some function of U means that I see your payoff. I want to get at least something that depends on your payoff. And they also can pin down, they find a control problem that finds R, and they can find R. So they can run a control problem that its solution is this optimal R. If randomized mechanisms if randomization is allowed, then what you can get using their argument essentially is that eta UV is monotone in U. In V, monotone increasing in V. See, this is the analog of this thing for random, for a probabilistic function, but I don't know, it seems like very difficult to actually find the optimal eta. Okay, it's a function of 2 variables. So this is the state of the art, I think, for the case of Bayesian mechanism. And now I'm going to describe to you the optimal mechanism with randomization in case of in case that randomization is allowed. And
Eran, you've got a little less than 10 minutes.
Yes, I think I'll be fine. So let's try to find the mechanism. Let's look for a mechanism with, sorry, my handwriting become, with worst case regret R. Suppose that I'm trying to find a mechanism with worst case regret R. The main thing you want to remember from this talk is that the principal has two fears that eats him. One fear is that if I accept with low probability, then I'm going to, I accept with low probability, then it may be that I'm losing the, all the probability in which I could have accepted, I'm losing, right? The other thing, if I'm accepting with high probability, then maybe the agent is hiding something better for me, right? How does this thing manifest itself? If agent proposes UV and V is smaller than 1 minus R, then I am worried that another project is available, a project that gives the bad payoff to the agent and the good payoff for me. What does it mean? A project that is even, this is the project, it means that I could have gotten one, right? And the agent maybe is hiding this thing. And if this thing exists, then my regret would be higher than R, right? Because the agent here offered me a project with V smaller than 1 minus R. I must make sure that the agent would not pick this, right? I must make sure that the agent, so I must make sure that the agent would pick this. Sorry, I must make sure that I am accepting with sufficient, that I'm accepting this project with sufficiently small probability such that the agent will never hide this project. And in order to do that, from this project, from the project that I now put in circle, the agent can get M, right? At most M. I cannot give the agent, therefore, more than M if he's offering me the red project, right? Because if I will give him more than M, if he offers me the red project, he will hide the black project, right? And all these things I told you in order to say that, sorry, that that eta UV must be at most M over U if V is smaller than 1 minus R. I cannot accept with high probability because if I accept with high probability, the agent will hide the black project. And if V is greater than 1 minus R, I can, in principle, accept with probability R, with probability 1. Okay. This is the maximum that eta UV can be. Well, maybe that's it. Maybe for every R, we can create this mechanism and get a mechanism with worst case regret R. Of course not, because we have the other problem. We have the problem that now these projects we accept with maybe too low probability, right? We may create regret if the project, if the only project that is available is a project that give the agent something and give me V. This is the only project that is available, and I am accepting it only with probability M, right? According to this formula, I'm accepting this project only with probability M, then I create regret of 1 minus M times V, right? And if V is 1 minus R, then I'm creating this regret. Okay, so I may create, by using this mechanism, I may create this regret, and the optimal R is the one that solves for this equation. Okay, so R solve this equation. The optimal R turns out to be something that I would have told you the formula if I had time, but I think it turns out to be 1 divided by 2 plus M, but I'm not sure. No, sorry, it's not this. Okay, so I don't remember the optimal R, but this is the optimal R that it solves, and this is the optimal mechanism. Okay. And what I wanted to tell you about this mechanism is that eta uv is increasing in V, as we saw before, but also eta uv is decreasing in U. It's decreasing in the agent's payoff. This is new. Why does it happen here? Why it is decreasing in the agent payoff? Precisely because if the agent proposes a project which gives the agent a high payoff, I am more worried that he's hiding something that gives me a high payoff. And my only way to deter him from offering a project that gives himself high payoff is to decrease the payoff that he gets when he offers this project, and I do this by decreasing the probability of acceptance. Okay, so this is what I had to say about the optimal mechanism with randomization. 2 more minutes.
So
yeah,
can I ask, so M here is just the highest amount that the agent can get consistent
no, it's
with
the lowest amount that the agent can get. M is the lowest amount.
Consistent.
It's a lower bound on the agent's payoff, which is a simple
lower bound on the agent's payoff. Did I confuse you, Steve?
Yes, no, I got it now. Yep.
Good. Okay. Okay, so I'll just tell you how the mechanism look like if the principal can only observe V. Only observe his own payoff, then actually the optimal mechanism divide the interval to infinitely many small intervals. In this interval, you accept with probability 1. In this interval, you accept with probability m. In this interval, you accept with probability n squared. And the intervals are built such that exactly if the agent has projects from this interval, even if he gets the worst possible payoff here and the best possible payoff here, even if he gets the worst possible payoff here and the best possible payoff here, he would still make worst case regret at most R. Okay, and I could have compared the payoffs, but you see the structure of the mechanism becomes something completely else, precisely because I cannot punish him by knowing his utility. I can only use on my own utility. In conclusion, 1 minute, then the worst case regret approach gives you more in terms of tractability here, in this problem at least. It allowed us to identify the benefit of observing the agent's utility in this project. The optimal mechanism decreases in the agent utility if we observe it, and if it doesn't, you get a different structure of optimal mechanism. Thank you. I think I'm on time, right? And excellent. I will stop sharing.
Excellent timing, and also time for questions.
You mentioned this that you could generalize the set D beyond the rectangle. You want to say something about that, or?
So for everything I said today, the thing that I really needed is the existence of this project that was the worst to the agent and the best to the principal. So as long as this project exists, this project M1, which I appealed to several times, then everything I said today goes through. Otherwise, you can still solve, but you can still solve for the optimal mechanism using the same method. But this specific point that I highlighted, the fact that the utility is monotone decreasing in the agent's utility, that doesn't necessarily hold.
Okay.
Sergio?
Yeah. So the crucial factor here is really M, because if when M goes to 0, you are going to get nothing. Your regret is going to be 1, and you will complete. So the
it's
whole
not going to be 1. It's going to be half. But yes, it's going to be half. But yes.
Sorry.
Yes.
The regret. I
half.
think the regret is going to be 1. No, it's going to be 1.
No,
if M is 0, to be a half. No, I think you are going to get nothing. Nothing out of this mechanism.
If n is 0, I will accept a project if it gives me at least half, and otherwise I will reject it.
You are talking about the second. I'm talking about the first part where you see U and V.
Yeah, also in the first part. But anyway, yes, you're right. It's very important here that M is greater than half. It's not. It's that M is greater than 0. Otherwise, it's trivial. If you stay next week for the workshop, you will see that even for M equals 0, the randomization does help you in case that the agent offers a bunch of projects.